this video, we are going to define the wedge product of one-forms. So what is the point of the wedge product? Well, I would say one major goal of ours is to take the notation dxdy or dxdydz from multivariable calculus and turn it into something that's on a precise mathematical footing, something we can actually integrate and we know what that means. And wedge products will enable us to do that. But I'd say don't hold your breath until we actually integrate differential forms, because that will be in a few chapters. So basically, the wedge product multiplies one-forms, and the result is some higher form. So not only are there one-forms, there are k-forms for any k. So maybe I won't stop at 2. K equals 1, 2, 3, 4, etc. K equals 5,000. There are k-forms. And a one-form, we know that it's a function where at a point in Rn, it eats a vector and spits out. So it's a function that goes from Rn to the dual space to the tangent space at a point of Rn. So a one-form is a function from Rn to the cotangent bundle, and it sends a point P to some element of Tp star Rn, and elements of Tp star Rn, recall, so let's call our one form alpha. Alpha at P is going to take something, is going to be a function from Tp Rn to R. So alpha at P is going to eats vectors in TPRN and outputs numbers. So a k-form are basically going to soup this up. So k-forms eat k vectors in TPRN and output a number again. So k vectors turn into one number. So the simplest type of k-forms are going to be the wedge product of two one-forms. So what do we want this wedge product to do? How do we want to generalize one-forms to two-forms? So notice that if my coordinates are x1 through xn on Rn, then dxi at a point P, so this is just the sort of coordinate one-form, if it eats a vector v sub p in the tangent space to Rn at P, it's going to output the length of the projection of v sub p onto the xi axis in the tangent space to Rn at P. So how would I like to generalize this to something that eats two vectors? So the idea is that dxi wedges dxj at P. So this is where the wedge product gets its name, as we denote it with this wedge, is going to eat two vectors, Vp and Wp, elements of the tangent space to Rn at P. And this is going to be the area of the projection of the parallelogram spanned by Vp and Wp to the xi, xj plane in TP Rn. So how can I make this precise? This is actually the area of the parallelogram spanned by the vectors dxi at P applied to v sub P, dxj at P applied to v sub P, that's a V, not a P, and dxi at p applied to w sub p, dxj at p applied to w sub p. And this is just because when I want to project v sub p to the xi xj plane, right, I should take the coordinate, the length of the projection onto the xi axis and the length of the projection onto the xj axis, similarly with w. Okay, but now how do I compute this area? Well, that's my old friend, the determinant, right? The area of a parallelogram spanned by two vectors in R2 is just the determinant of the matrix where those two vectors are the columns. So that's easy enough. So I'll just remind you that this is how we define dxi wedge dxj at p applied to v sub p and w sub p. So this is our definition of the wedge product of two one forms, of two one forms that are the coordinate one forms. So let's do an example. So in R3, let's let v sub 0, 0, 0 be the vector 1, 1, 1 at 0, 0, 0. W is 0, 0, 0. I'm going to just use a single 0 to denote the origin to be negative 1, 1, 2. And I want to compute dx wedge dy at the origin of v at the origin, w at the origin. So this is the determinant of the matrix. Well, okay, so the top left entry should be dx applied to v naught, so that'll be 1. The bottom left entry should be dy applied to v at 0, so that'll be also 1. And then the right column, the top entry should be -1, and then the bottom entry should be 1. Oh, whoops, taking the determinant. So this is 1 plus 1, which is 2. So let's compute dx. Let's compute dy wedge dz at 0. So I need to apply dy to v, so that'll be 1. Apply dz to v, that'll also be 1. Then for the top right entry, apply dy to x, so that'll be 1. Or sorry, to apply dy to w, and then apply dz to w, so I'll get 2. So this is 2 minus 1, which is 1. And another simple example, let's just do dy wedge dx at 0, b0, w0. Oh, notice that for my differential form, so this is an aside, for my differential forms, I either use dy wedge dx at the point 0 like this, or with a subscript. And I'm not taking the wedge product of dy at 0 wedge with dx at 0. I'm really considering dy wedge dx as a new differential form and taking its value at 0. I mean, none of this really matters for these differential forms because they're very simple, the coordinate forms, but for more complicated ones we'll see later, it will matter to be precise. Okay, so basically the matrix I get here should be this matrix, but with the column switched, applying dy to v, with the rows switched. So apply dy to v, get 1, apply dx to v, get 1, apply dy to w, get 1, and dx to get -1. So this is going to be -2. Okay, and so we had this definition of the wedge product of coordinate one forms. There's an obvious analogy. So generally, if I have two one forms, alpha and beta, at P, their wedge product applied to VP, WP is the determinant of the matrix. Alpha at P applied to V at P, beta at P applied to V at P, alpha at P applied to W at P, and beta at P applied to W at P. So basically you should think of the wedge product as like, think of all the ways you can combine, evaluating alpha on v and w and evaluating beta on v and w in some geometrically meaningful way. One other thing to notice is this distribution that happens, which is because the determinant is linear in the rows and the columns. So if I have, for example, you can generalize this, but if I have dx plus dy, and I want to take the wedge product with dz, and then I want to take it at a point P and apply it to v and w, then this is the determinant of dx plus dy at P applied to v at P, dz at P applied to v at P, dx plus dy at P applied to w at P, and dz at P applied to w at P. And then just by the linearity of the determinant in a single row, I can write this as dx at P applied to v at P, dz at P applied to v at P, dx at P applied to w at P, dz at P applied to w at P, plus dy at P applied to v at P, etc. So this is then dx wedge dz at P plus dy wedge dz at P, all then applied to v and then w. So in this sense, we kind of think of it as multiplication, right? Because we have this sort of distributivity that we have when we multiply numbers. Another thing to notice is I guess I wouldn't call it anti-commutativity. So if I have alpha wedge beta at P and I apply it to V at P, W at P, or maybe let's think of it as beta wedge alpha. This is some determinant of some matrix where I apply alpha. So I'm going to just drop the subscripts just for ease of notation. So this is beta, then alpha, beta, then alpha. So because the determinant satisfies the property that if I switch any two rows, I introduce a minus sign, I can switch the top and the bottom row. And then this just gives me back alpha wedge beta at P, V, W, but with a minus sign. So when I switch the order, I get a minus sign. So we're going to denote by this big wedge of Rn, the space of differential two forms on Rn, which is precisely, so these are linear combinations with coefficients which are smooth functions on Rn of wedge products of one forms. So elements are, of course, things like dx wedge dy at P, but I could also take, for example, my example dx plus dy wedge dz at P. And then what did I mean by this coefficient smooth functions on Rn? Well, I could do something like 2y dx wedge dy at P. So I can multiply my two-form dx wedge dy by 2y, and then basically just apply, the way I evaluate this is I just apply dx wedge dy and then multiply by 2 times y, where y is, the y coordinate of P. And then maybe, I can take linear combinations. So I'll make this then, I'll add e to the x times dx wedge dz at P. So those are examples of elements of big wedge 2 of Rn. And more generally, we define big wedge K of Rn to be the space of differential K-forms on Rn. So basically, in this definition, replace wedge products of one forms with K-fold wedge products of one forms. So how do you take the K-fold wedge product of one forms? Well, it generalizes as you would expect. Alpha 1 wedge all the way out to alpha n at P, applied to V1 at P, all the way out to Vn at P. So here, notice that I'm using this sort of functional notation for vector fields and one forms, is defined as the determinant of the matrix, where just do sort of the obvious generalization. So apply alpha 1 at P to V1 at P, apply alpha 2 at P to V1 at P, etc., all the way to alpha n at P, V1 at P, and then alpha 1 at P, Vn at P, alpha n at P, Vn at P. So this is how I define the wedge product of more than two forms. Notice that, again, that if I switch the order, right? So say I have like alpha 1 wedge all the way out to alpha I wedge all the way out to wedge all the way out to alpha j, then if I were to switch the order of, so I'll just do this for the sort of the simplest possible case. So if I have alpha 1 wedge alpha j and they're right next to each other, and then I switch their order, that's I get a minus sign. So if I switch this to alpha j wedge alpha I alpha n, and in general, if I were to permute all of the alphas, then I would change the sign of my wedge product by the sign of the permutation. And notice that this means that that if I were to repeat any two alphas, I would get 0. So in the k equals 2 case, alpha wedge alpha is equal to minus alpha wedge alpha, because if I switch them, it looks the same. But then this implies that alpha wedge alpha is just 0. And more generally, if I repeat any alpha I, the wedge product is 0. That's because I can do this switching procedure until I've moved my my two repeated factors next to each other. Then when I switch, I get basically the same equation as right here, which when I add this side over to this side gives me 2 alpha wedge alpha equals 0. So alpha wedge alpha has to equal 0. And the final piece of final definition I want to make in this video is that the n form dx1 wedge dx2 wedge all the way out to dxn on Rn is called the volume form. And this is basically because when I apply this volume form to any n vectors, I'm going to get the volume of the parallelepiped spanned by those vectors in the tangent space to Rn.